Hi, we're going to talk about complex zeros and the fundamental theorem of algebra. So, the fundamental theorem of algebra states given a polynomial with real or complex, there's at least at least one complex zero. Okay, so this is what your book writes. And, and apparently I was intelligent enough, and I wrote it in plain English. This means, in essence, the polynomial factors completely, because if I can pull out one complex zero or one zero whatsoever, complex or not, right? um, I'll get another polynomial, and that will have at least one zero. So I can pull that out, and then I'll have another polynomial, and I can pull that out until I have it completely factored like this. Okay. And so that means you can completely factor every polynomials with at least complex numbers. Just something real quick. Um, the real numbers, the reason we have to introduce complex numbers because we call it the algebraic closure. And that means given a polynomial with real coefficients, it'll have it may have real coefficients or complex coefficients, but it won't have anything else, right? There won't be anything beyond that, right? And so we call that the algebraic closure. There are other numbers beyond complex numbers, um, and believe it or not, right? If I have integers here, if these are strictly integers, I do not have to go all the way to the complex numbers. You can do really fancy complex integers and close it, but that's for much more advanced class. But the reason we introduce complex numbers in the first place, the whole point of they exist is so we can find zeros here, right? Now, do we use them all over the place in engineering? Sure, right? It's the extinction coefficient for, when light penetrates into objects, right? And all this other stuff. And so it just pops up everywhere. However, the reason math invented it is not why we can completely factor this, right? That's the reason why math invented complex numbers. Okay, so given that, we're just going to do the same thing we did in the last chapters. We're just going to now factor things that may or may not have complex zeros. And we're just going to do all our, and we're going to do all our, um, and we're just going to use all the tools we have available. All right, so if I wanted to factor this completely, does anyone know what I would do for this one? If I wanted to factor this one completely, just start, just start free here and start guessing things and start factoring. Is that what you guys would do? Probably. No. Grouping. Hey, someone got grouping. This is a factor by grouping. Notice here, we no longer tell you to factor by grouping, but notice here I have 1 and -3, 1 and -3. So we can factor by grouping. So here I have x minus 1 plus -3, or hold on, that should be a 3. Whoop. Hello. I'm on the wrong layer. I think that's probably the most quoted thing in my notes. I'm on the wrong layer. Plus x minus 3. So if I factor out the x minus 3, I get x minus 3. There's a technical 1 here, and so this will be x squared plus 1. Okay. Now, here I get x minus 3. If I want to factor this completely, right, notice here that this is x squared is equal to minus 1, so x is equal to plus or minus I. And so my complete factorization here is x minus 3, x plus I, x minus I, and my zeros are the following. I have 3 and plus or minus I. Okay, so when it comes to factoring, just go ahead and use all the tools you have available. All right, for this one, I give you a hint. Use x is -2 as a factor. And so here we're just going to use the hint. I guess I gave myself a hint. It's terrible, but just I didn't leave that much space for all the guessing. So here we have 1, -2, -2, +4, -2, -4. That's a +2, sorry. Um, and 0. So that factors cleanly. So here I have x x minus or plus 2 x squared minus 2x plus 2. Okay. All right. Does this factor nicely? And the answer is no. You just use the quadratic formula. So here I'll have x is equal to 2 plus or minus the square root of negative 2 squared plus or minus 4 times 1 times 2 all over 2 times 1. So this becomes x equals 2 plus or minus square root of negative 4 over 2. And so x is equal to 1 plus or minus I. So the square root of negative 2. Pull out the 2, so it'd be 2 square root of negative 1, or 2i divided by 2, so just I. And so here we have our factors here of x plus 2, x minus 1 minus I, and then x minus 1 plus I. Okay, and here are zeros, we can list them out. So here I have my zeros of negative 2 and 1 plus or minus I. So one thing that we know is the conjugate zero theorem. If a polynomial has real coefficients, and this is only if it has real coefficients, you won't really deal with anything that doesn't. Even in engineering, you probably won't, right? You may, but then complex zeros comes a pair of conjugates. And so say the pair of conjugates from the above example. So from this example, my conjugates were z equals to I, and then z equals to minus I, right? So here I had positive, I had I, and then its conjugate, negative I. And remember, conjugate is just a little bar over it. If you need a review, go back to what, 1.6 b, or here b, my conjugate. So if my z was 1 plus I, my conjugate here was z1 minus I. And so notice how we have both here. Okay, so I think complex numbers for polynomials with real coefficients, if there is a complex number, you're going to get a pair of them, right? They're going to come as pairs. Another way of saying this is you can factor a real polynomial with at least quartic or quadratic factors. So if you pull out quadratic factors, because the complex pairs will end up being a real quadratic. But you just want the zeros, and so we'll end up doing that. Okay, let's go to the next page. Today is just a bunch of factoring. That's all we're doing. And then we'll do two kind of unrelated sections next time that will help us to do all this. So zero theorem. Every polynomial of degree n greater than 1 has exactly n zeros, counting multiplicity. So if we count the multiplicities, or how many times it's a factor, we'll have exactly n non-zeros. And so you know how many you're looking for and what to do. Okay. So here, let's factor this one completely. And here, we're gonna use the x squared. Remember that little trick I showed you using x squared? And so just pretend x squared is x, and so we have an x and then an x squared here, or x squared squared plus x squared, so I can factor like this. If I do this, I'll get minus 2 and positive 4. Yes. Because here, if I do this, I'll get x to the 4th. I'll get minus 2x squared plus 2x plus 4x squared, which gives me 2x squared, and then that'll give me negative 8. Okay. All right, if I'm going to completely factor from here, so remember this is x squared is equal to 2, and this is x squared is equal to minus 4. So that means x is equal to, or at least if I set these equal to 0, right? If I set this equal to 0, that's what I'm doing here in my head. If I set this equal to 0, find the factors, here I will get plus or minus the square root of 2, and then here I'll get plus or minus 2i. And so all the factors here would be plus square root of 2, x minus square root of 2, x plus 2i, x minus 2i. And so this is factored completely. And so, and then we're going to type in our zeros. So our zeros here are plus or minus 2i, and then plus or minus square root of 2. And these all have multiplicity of 1. Okay. All right. So let's go ahead and do this one. So here, notice how I have an x everywhere. I don't have a constant term. If I don't have a constant term, you can cleanly pull out an x. In fact, in this case, I can pull out a 3x, right? I can cleanly pull out a 3x. And that leaves me with x to the 4th plus 8x squared plus 16. Yeah. Okay. And then here, I can use the same trick we did here. So I have 3x. And this will be x squared plus 4. This will be x squared plus 4. Do I know what this factors into? Yeah, it factors into plus or minus 2i. So this is 3x plus x plus 2i, x minus 2i, x plus 2i, x minus 2i. Okay? So this turns into x plus 2i and x minus 2i. This turns into x plus 2i, x minus 2i from here, right? We already did this. So what are my zeros? So my zeros here are, well, 3x, that's just my zeros, sorry. I said 3 and then my brain's like, oh, let's draw 3. No, not yet. 0. And then we have plus 2i and then minus 2i. And I'm going to go ahead and leave those separate. And I'm going to write the multiplicity, just right down below, just as mult. So the multiplicity of this is 1. The multiplicity of this is 2 because I have it twice, right? And the multiplicity of this one is 2 because I have it twice. Okay. And so what's the polynomial? This is 3, 5, and I have 1 plus 2 plus 2, so that is 5 zeros. And here I have 4, and I have 1, 2, 3, 4. Okay, so a polynomial degree n, you know exactly. So if I give you x to the 47th minus, x cubed, you know you're looking for 47 different zeros. Now, I'm not going to do that to you, right? But that's just something to know. Okay. Another way of writing this is you can have a polynomial with real coefficient can be factored into linear and irreducible quadratic factors with real coefficients. Let me just kind of show you what that means. So state the real and linear quadratic examples from above. So here, if we wanted to factor without complex numbers, you can. So you'll just have linear factors and quadratic factors, or irreducible quadratic factors. This we can reduce in the reals, right? And so for A, we can reduce x plus square root of 2, x minus the square root of 2. We could reduce that in the reals and still be in real, right? These are real numbers, right? This is x plus 1.4 something, this x minus 1.4 something, right? But this term, we cannot reduce, right? At least it'll still be real, right? And so we just rewrite it as this. Every now and then, you're going to want to have all your factors be real for who knows, for some reasons, right? This is just another way of saying I can factor. Here, notice here when I'm at the 3x plus x squared plus 4 plus x squared plus 4, here I've had it into my irreducible quadratic factors, okay? Another way of you can also write this as x plus x squared plus 4 squared. And that's also another popular way to write factors. In fact, we can also write this as 3x plus 2i squared plus x minus 2i 2I squared. And this is actually quite a popular way, instead of writing them out one at a time, just to write it this way. And that way the multiplicity of this 0 is whatever factors here. So 2 and 2. So this has multiplicity 2 and 1. Okay. All right, I'll leave this v for a second, and then we'll do a little bit more practice, and then we'll go from, and that's it for the day, actually. I have another friend. Okay, all right, I got you marked as late. Okay, you're all in the class. All right. All right, let's do the last page. So let's put everything together. So here we have factors, completely state and completely factor, and state to 0. So that's basically, if you can do that, you can do anything you want to do with all numbers, more or less. I guess that's not fair. So here, let's go ahead and do this. So here I can factor this into x squared plus 4 x minus 4. I guess I already did this one, so I probably should rewrite this problem for next time. But here, I know what my zeros are. They're x plus 2I squared, x minus 2I squared. And so, oops. Woohoo! I'm on the wrong layer. Always on the wrong layer. Woo. So this is x plus 2I squared, x minus 2I squared. And this is from before. And so the zeros here are 2I and minus 2I, and we have, let's say, the multiplicity here for each of these is 2 and 2. Okay. All right, so let's do, that one's kind of fun, interesting. Let's do this one. All right, so here I give you two of the answers. So let's go ahead and do that. So here, I have -3 and -3. And here I write it twice. That means try it twice. So notice here, if I tried all the factors of this, I'd find all the factors of 36 and test them out. So I do 1, -1, 2, -2, 3, -3, 4, -4, and just all the way up, right? So here, but I tell you which ones work, just to kind of help for these of doing it. But as I showed you last time, just go ahead and try them all. So here, if I do this, just do synthetic division. 1 minus 3, 3, add that up, get 3, get minus 9, add that up, I'll get 4, that'll give me minus 12, that'll give me positive 12, sorry. 24 plus 12, plus -12 is positive 12, which gives me minus 36, which gives me 0. So this is x minus 3 equals actually, here, we don't even have to do that. Let me show you. If you're doing this on your own shorthand version, just go ahead and take this and just drop it down. You don't have to write it out. Does that make sense? You don't have to write it out and then redo it. Just take this and drop it down. I've seen some students just do this after they get a 0 and just keep trying other things. That's fine too. But go ahead and just rewrite this. Here I get 1, -3, 0, 0, 4, minus 12, 0. And so here, what do I have? I have x minus 3 times x minus 3. And then here I have x squared plus 4. Do we know what x squared plus 4 factors into? Yeah. So here, if we factor completely, x minus 3, I'm going to write that as squared, x minus 2i, x plus 2i. So my zeros here are -3, 2i, minus 2i, and the multiplicity of them is 2, since I have it twice, right? Or here, as I've written it as a square, right? 1 and 1. And is that how many I should be looking for? Yeah, here I have x to the 4th. Okay. All right, let's handle this funness. I'll zoom out so everyone can copy at the end. All right, so here if we have this, what do we need to try? Well, we need to try everything here. So, so here if we tried everything, it'd be 1, -1, 2, -2, 4, -4, and then 1/3, -1/3, 2/3, -2/3, and then 4/3 and -4/3. Are all the I'll give you which ones work out, 2 and -3. So let's just do it in that order. In practice, you just have to do them all. So it'll be 3 minus 2 minus 1 minus 12 minus 4. And by the time you're done with all these sections, you're going to be very good at either synthetic division or just typing stuff into Wolfram Alpha. I'm just going to be honest. I know half of you will do it, right? Try to do some of them by hand. That way you get doing stuff by hand helps you to build intuition, which is invaluable as an engineer when it comes to math. So do a couple by hand. Do check it in the computer, of course, and manage your time. You know how much time you have to do some things. Okay. All right. So here we have 3. This becomes 6. This becomes 4. This becomes 8. This becomes 7. This becomes 14. This becomes 2. This becomes 4. This becomes 0. All right, so we're just going to drop that all down. But now we're going to do this for the first time with a fraction, right? And this is going to be fun. So 3, 4, 7, 2. This looks like it's going to be some awful mess, right? But it ends up not being that way. So this is 3 times a -3rd is -1. Add this up, I get a 3 times a -3rd is -1. Add this up, I get a 6 times a -3rd is a half. -2, 0. So what do we have here? We have x minus 2, x plus a third times 3x squared plus 3x plus 6. Here, factor out the 3. Factor out the 3 just to make your life easier. Achoo! Okay. So here we factor out the 3. Thank you. And here I get x squared plus x plus 2. Notice here there's nothing. I cannot make this cleanly, right? This doesn't factor. You think does for a second, oh, it's just 2 and -1, right? But that ends up being -2, not +2. So here we have to use the quadratic formula. So this is -1 plus or minus the square root of -1 squared minus 4ac, which is 2, all over 2a, which is 1. This simplifies out to be -1 plus or minus square root of -7 over 2. So I get x is equal to -1/2 plus or minus square root 7 over 2i. It's just awful, right? There's just no other way to describe that. It's just awful. So let's write out our factors completely. So x minus 2, x plus a third. Here, if this is this, it'd be x minus all this. So it'd be x plus a half minus square root of 7 over 2i. And then x plus a half plus square root 7 over 2i. So what are my zeros? So my zeros are the following. 2 minus 3. I just realized that I always keep putting apostrophe s. I probably should not put the apostrophe. Anyways, we'll worry about my lack of English skills later. And these all have multiplicity of 1. So they all have a multiplicity of 1. They only appear once. Okay. All right. Well, that's it. So now, given any polynomial, over these last couple sections, we've kind of introduced more and more things of how to factor and work things out, you know, how to deal with complex numbers, how to not deal with things. And so at this point, a polynomial of any size, you can find all of the zeros, right? You know how to look for the rational ones, you know how to find complex ones. If they're all irrational, just use a computer, right?